Hello everyone and welcome to this new video where we're going to practice what we learned in the RNN architecture. So we're going to do a simple project where we have a data set of the minimum temperature of the of specific day for 9 years, and our goal is to predict the next day's minimum temperature. So as I said, the objective is to build a time series forecasting model that predicts the minimum temperature of the next day based on the sequence of the past temperatures. And when we hear the word temperature or memory, we know that we're no longer using a simple vanilla neural network, but we have to use more advanced architectures. So the dataset would be this one from GitHub. It's the minimum temperatures in a city in Australia from 1981 to 1990, and the temperature is in Celsius. So we can see this data set. We have the date and the temperature from the 1st January 1981 all the way to 31st December 1990. So the first thing we do is obviously get the data, transform it into data frame. Then we have to see some of the properties and statistics of the data. So these are the first 5 rows. So what we did was correct. For the info, we have no null values, non-null, this one. The type is float. And then we can see some statistics like the count, mean, standard deviation, etc. Let me run this again. It's connecting to the GPU. Okay, moving on. This line here is just to double check that we have no null values. Is null.values.any, so it's in fact correct. Next, let's visualize the data. I just plotted the data here. This is the daily minimum temperature in Melbourne, the city. We can see it's fairly consistent. It goes down then up in a consistent range, so we can say this time series reverts to mean or stationary. And if we zoom to a specific year, for example the first one here, we can see that it goes down in the 5th to the 9th month of the year and then goes back up. So the idea here is, let me open Paint. The idea here is that I'm going to take the last 2 years and use them as a testing set. So I want the RNN to train based on all of this data here, and then train on this one here. To do that, we have to do the data pre-processing. This is just in case. We've seen already that it's a float, but it's a good practice to always change the type if there are some values that are integers or something else inconsistent. So then we set the test size to the last 2 years, as I said. This is to check. These are like 2 years worth of data, which is 365 times 2. And the train sample is the previous years. And then we would scale the data from -1 to 1. Normalize them. And this is here the sliding window method. How we're going to train the model to predict sequence is we give it the first month worth of data and we want it to predict the 31st day, so it has 30 days to learn from and then predict the 31st day. Let's see if we can. So here 30 days, let's say this is 30. It would train on all of this and then try to predict the 31st, and then of course with the loss, the difference between the actual and the predicted, we would adjust our weights and biases and then do the same thing, move on 30 days and then 31st day. So the second iteration would be from the 2nd to the 31st to predict the 32nd day, and so on and so on. Okay, this is the train window, as we said, 30 days. Then we create the training sequences. We have 2830 training sequences. This is just to check the shape, as we said, the 30 days worth of sequence, and the label would be the 31st day, or the size 1 because it's 1 day. Next, we do the model architecture. So we have the hidden layer, the RNN layer, fully connected layer, and then we do the forward pass. Let's run these cells because we did not. Okay. I think this one is okay. So for the RNN, if we want to visualize it, it's something like this. We have the input, the first day, let's say. It goes to the hidden layer and then goes to the second hidden layer. We said that the hidden size is 64, and then of course in each hidden layer we have the input, and then like this we move using the weights and the biases until we reach the final one, and then we make the prediction. Okay, and then let's run this. This should be okay. Then we move the model and everything to the GPU for faster training. Then we create the tensors and data loaders for the PyTorch, because that's what the PyTorch expects. And here we start training. We train. Training, as we said, is we do forward iteration and then go back with back propagation through time. So we completed the training in 6 seconds almost. We've set, this is an important thing, we set the shuffle true because you can say that we cannot shuffle through time steps, but in fact we do. It's because when we shuffle the order of the batches during the training, it prevents the model from over optimizing for specific years in order to help generalize the physical laws of temperature fluctuation. So basically, so it would not overfit. Now here we are interested in evaluating the model by testing the loss, or we've converted the loss to the Celsius, because that's the unit that we're working with. Of course, using the test dataset, the last 2 years, I mean, that we separated earlier. So the loss is we're having a difference of 2.24 Celsius on average. We can also plot this. We can see that the predicted temperature is hugging the actual temperature, so it's not far off. It's just that when we have a spike in the upward direction or the downward, it fails to immediately goes down or up, which is good, because if it was exactly like the blue line, we would have doubts of overfitting. So yeah, if we zoom in on the first 50 days of predictions, we can see the same thing that we said when it goes up very fast. The predicted temperature fails to immediately also goes up. Here we will use the granular training to see the noise, and see also how quickly the model converges to a stable solution by memorizing the history. Let's see the graph. We can see this is the blue line is the moving average, and the almost green transparent is the batch noise. We can see that we've started with a relatively high loss, and then we very fast go down, and then we almost stabilize, but we still have fluctuations, because here the model very fastly predicts the pattern, but here it is trying to also learn how the small fluctuations work. This is the noise, or the fluctuations in the blue line. Now we said that the RNN has a big problem of the exploding or vanishing gradient. So here I'm trying to visualize it, because remember we said if the weights matrix are greater than 1, the product would grow exponentially. If it's less than 1, it would approach 0. This is the case that we will visualize now, because remember that for each back propagation we would go this way, and because this depends on the previous one, remember the memory, if we have a small value here, it would be multiplied by a small value, which would get even smaller, until we almost reach 0, and the model would not actually learn anything, because each step would be very, very small. So here the key is that we put the weight less than 1 here, so it's 0.8, starting with 0.8, we will see what would happen. Weight is not defined. Wait, it's not defined. Oh, this should be a comment. So we can see because backpropagations goes in the opposite direction from the future to the past. Remember, we go from the 30th day to the first day. We can see if we start 0.8, it gets really small very fast until we are here at almost 0. So the left plot confirms that the standard RNNs, the learning signal or the gradient, decays to 0 quickly, making it impossible for the model to remember events from, let's say, 50 days ago. So to fix this, we need to upgrade to the long short-term memory or gated recurring unit, which uses internal gates to protect the gradient flow over the long sequences. So that's all for this video. Thank you for watching.